So this video lesson is about intermolecular forces. So when we're looking at intermolecular forces, the first thing that we want to do is to figure out what intermolecular forces actually means. So the most important part of the word is the inter. So inter actually means between. So intermolecular forces actually mean forces that are happening between molecules. So if we want to draw what that looks like, if we were to draw a molecule of HCl and then have a separate molecule of HCl, so we have these two molecules of HCl, they can have a force of attraction between them, and that is an intermolecular force. So one HCl molecule is being attracted to a different HCl molecule, and that is our intermolecular force. Now there is such a thing as intramolecular forces, and that's actually what's going on within the molecule. So this is an intramolecular force. So intramolecular force means within the molecule, whereas an intermolecular force means between molecules. And so when we are drawing pictures of intermolecular forces, we need a minimum of 2 molecules. Because in order for us to draw something that's happening between objects, we need at least 2 objects to show what's happening between them. So we need at least 2 molecules. We have to be drawing at least 2 molecules so that we can illustrate an intermolecular force. Now, there are actually 2 different types of intermolecular forces. So the 2 different types are ionic forces and van der Waals forces. So we're going to start with ionic forces, and we're going to come back to those van der Waals forces. So these are the 2 different types of intermolecular forces. So ionic forces are attractions between permanent charges So an example could be when we're looking at our salt. So we know in salt we have sodium and chlorine. And the sodium has a positive charge and the chlorine has a negative charge. And they're attracted to each other. That's an ionic force. So it is a type of intermolecular force. And it is a positive charge being attracted to a negative charge. So they're ionic forces of attraction. Okay. These are happening in every ionic compound that we're dealing with. So if we have an ionic bond, that means we have an ionic force. So our ionic bonds are really just ionic forces of attraction. Okay. Those ionic forces are happening between permanent positively charged things and negatively charged things. So happens in any other type of ionic compound as well, where we have a positive charge and a negative charge. Doesn't matter if it's +1 or +2 or +3, and it also doesn't matter if it's -1 or -2 or -3, as long as those charges are real, actual charges, and they are permanent. Okay, and that's going to happen in all of our ionic compounds. All right, now the difference between ionic forces and then our van der Waals forces. So if you look back at our van der Waals forces are attractions between partial charges. And so in ionic forces, those attractions are happening between positive charges and negative charges. In van der Waals forces, they're happening between partial positive charges and partial negative charges. So we're still getting an attraction, But the attraction is not between a positive and a negative charge. It is between a partial positive charge and a partial negative charge. Okay, and so our van der Waals forces are those attractions between partial charges. There actually are two different categories for van der Waals forces. So we can break van der Waals forces into two different categories. So the first are called London dispersion forces. And we just label those as LDFs because we don't like running London dispersion forces every single time we want to talk about them. So we have London dispersion forces as our one category for van der Waals forces. And then our other category are dipole-dipole forces. Okay, so we're going to have a look at those London dispersion forces first. So those London dispersion forces are actually in every molecule. So London dispersion forces are going to happen between any types of molecules, no matter what kind of molecule they are. One molecule is going to be attracted to another molecule because of London dispersion forces. And it doesn't matter what the molecules are. It doesn't matter how big or how small. It doesn't matter what they're made of. Every single molecule can be attracted to another molecule via London dispersion forces. Okay, so they're in every single molecule. And it's because London dispersion forces create partial charges. So we have created partial charges. Because of momentary unequal arrangement of electrons. Okay, key words in this is it only lasts for a very small period of time, so it is a momentary unequal distribution or arrangement. Okay, and so what happens is when we have molecules, so we're going to use a neon atoms as our example here. So we have some neon atoms. We know that neon has 8 valence electrons. And we also know that neon doesn't have a polar covalent bond, so it doesn't have a partial charge. Okay, and so we have these 2 atoms of neon. Now, when we distribute the electrons evenly, there are no partial charges between these 2 neon atoms, and so they will feel no attraction to each other. But at some moment in time that's a little bit later, we have these 2 neon atoms. Only in this neon atom on the left, we have most of the electrons are located on the right side of the atom. And the same thing is happening in our neon atom on the right. And so what's happening is for this split second in time, this side of the neon atom is partially negative, and the other side is partially positive. And the same thing is true on our second neon atom. So now we have a neon atom that has a partially negative side and another neon atom that has a partial positive side. And so then they can be attracted to each other. That's our LDF. Now, the tricky thing about LDFs is that they only last for a second and then they're gone again, because that electron the electrons being unequal is a momentary idea. So it only lasts for a moment, and then the electrons spread themselves out again. But the electrons are continually moving around. We know that electrons are always moving. And so the electrons are moving and moving and moving and moving and moving. And again, it might happen. And then they're moving and moving and moving, and it might happen again. And it can happen, a billion different times. And so LDFs are really weak because we only get that attraction sometimes. So it's going to happen over and over and over again, but it's not a predictable attraction. So we might have an attraction that lasts for a second, and then we'll have 5 seconds with no attraction, and then another attraction maybe lasts for 3 seconds, and then we'll have 20 seconds of no attraction, and so on and so forth. So it's an unpredictable attraction between those partial charges. But LDFs are in every single molecule because all we need to have LDF forces is to have electrons. And so every single molecule that we know of has electrons, so every single molecule has LDFs. All right, now if we go back up to dipole-dipole forces. So dipole-dipole forces are present in molecules that have polar bonds. So in order to have a dipole-dipole force, we need to have a polar bond. So we need a polar bond happening, okay? Dipole-dipole forces are also attractions of partial charge, but these ones are permanent partial charges. So they are not full charges, like in our ionic forces, but they are partial charges. But they are different from our London dispersion forces because the LDFs only last for a moment. Dipole-dipole has permanent partial charges. Those partial charges are there all the time. And so we're going to use an example of HCl. So we'll use HCl as our example here. So we have our HCl molecule. And we're going to draw a second HCl molecule because we can only illustrate intermolecular forces when we have 2 molecules present. And in our HCl molecule, we know that hydrogen to chlorine is a polar bond. So our chlorine is partially negative and our hydrogen is partially positive. So we have a partially positive hydrogen and a partially negative chlorine. And then when we have a partially negative chlorine next to a partially positive hydrogen, we can have our attraction. And so that's going to be our dipole-dipole. Okay. Now you'll notice that the dipole-dipole attraction looks almost the same as the LDFs. The difference is how the attraction was created, and the fact that LDFs are going to have that attraction for only a split moment, whereas dipole-dipole attractions are permanent because those are happening between partial charges that are never disappearing. Those charges are partially there because of the unequal distribution of electrons that's permanent in those molecules. Versus in LDFs, that unequal distribution of electrons is a momentary happening. Okay. So we have those dipole-dipole forces, LDF forces. Those are all van der Waals forces. There actually is one more, and it is a special kind of dipole-dipole. And it's one you might have heard of before, and it's called hydrogen bonding. So we've already split our intermolecular forces into ionic forces and van der Waals forces. Van der Waals forces has 2 different categories, LDFs and dipole-dipole. Dipole-dipole forces now have a special category that is only for dipole-dipole, and it is called hydrogen bonding. It actually works exactly the same way. So it is identical to dipole-dipole, but it requires specific elements. So it only happens with a few small specific elements. So there are 2 requirements in order to have this hydrogen bonding. So our first requirement is that we need to have a hydrogen that's bonded to either an oxygen, a fluorine, or a nitrogen. Our second criteria is that we need an oxygen or a fluorine or a nitrogen that's bonded to hydrogen. Both of those things have to be true for us to have hydrogen bonding. So hydrogen bonding, we're going to show some examples of molecules. So the three big molecules that we use that always have hydrogen bonding are NH3, HF, and H2O. Other molecules can have hydrogen bonding as well, but these three are usually the ones we use as examples for hydrogen bonding. So we're going to show the hydrogen bonding in H2O. And so we're going to draw our two molecules of H2O. So we know what our molecules of H2O look like. And remember that our H2O is polar. Our hydrogens are partially positive and our oxygens are partially negative. And so we can have an attraction between our partially negative oxygen and our partially positive hydrogen, and that is called a hydrogen bond. Okay, now the trick for this, so I'm going to draw it in purple here because I really want to highlight what needs to be occurring. So we need to have that partially positive hydrogen. It's going to be attracted to a partially negative oxygen, but that oxygen could have been a fluorine or a nitrogen and it still would have been hydrogen bonding. But then that hydrogen needs to also be bonded to either an oxygen, a fluorine, or a nitrogen. And that oxygen needs to be bonded to a hydrogen. So those four things have to be true in order for this to be a hydrogen bond. Okay, and again, that hydrogen bond is that blue line showing that attraction between a partially positive hydrogen and a partially negative oxygen. That's our hydrogen bond. Okay, hydrogen bonding is just like dipole-dipole, but it is stronger than a regular dipole-dipole. So if we want to actually compare our different types of intermolecular forces by strength, so if we put the strongest over here versus the weakest on the right side here, we're going to start out the strongest being ionic forces. Okay, and our weakest are LDFs. Okay, after ionic forces in terms of strength, we get hydrogen bonding. And then dipole-dipole forces. Okay, so ionic forces are the strongest. Hydrogen bonding is second, then dipole-dipole forces, then our weakest are going to be LDFs. Now there's one other thing about forces. So we also have increased LDFs when there are more electrons. Okay, the more electrons we have, the greater chance we're going to have that unequal distribution, and so we have more LDFs when there's more electrons. Okay, now why do we care about intermolecular forces? So the whole overview why intermolecular forces matter are because intermolecular forces are responsible for most physical properties of molecules. Okay, so that includes their boiling point or melting point, their solubility, as well as usually their hardness. Okay, so intermolecular forces are responsible for a lot of the physical properties of the molecules that we're going to look at. Okay, and one of the big things is that the more forces, so the more forces or the stronger the forces, the greater our melting points and boiling points. Okay. We can talk about this in terms of solubility and hardness as well, but we generally are using intermolecular forces to look at boiling points and melting points. So the more forces we have, or the stronger the forces are, the greater our melting point and boiling point will be. Okay, so we're going to actually have a look at two separate graphs here. And we're going to look and see if we can explain why the melting points are what they are in these graphs. Okay, so both of these graphs are going to be melting point of substances. And so we're going to have temperature on the y-axis. Okay, and so this graph here, so the melting point of CH4 is down here, a relatively low temperature. And then the melting point of silicon tetrahydride is up here. It's a little bit higher. And then we've got up here a melting point of germanium tetrahydride. And then a little bit higher here, we have our melting point of tin tetrahydride. And on our second graph, we're going to have a melting point for HF that is somewhere up here. Our melting point for HCl. And then we're looking at HBr. And then we're looking at HI. Okay, so in these graphs, we're just looking for trends in our melting point. So if we look at the first graph, okay, we look at CH4 compared to SiH4, GeH4, and SnH4. I hope what you notice when looking at your periodic table is that carbon, silicon, germanium, and tin are all in the same group. They're all in group 14. So all in group 14. Now, carbon has less electrons than silicon. Silicon has less electrons than germanium. Germanium has less electrons than tin. So tin has the most electrons, okay, which means tin has the most LDFs, which is why our tin tetrahydride has the highest melting point. Okay, so since the tin tetrahydride has much more electrons than the germanium, has much more electrons than the silicon, has many more electrons than the carbon, it has the most LDF forces because it has the most electrons, and that's why its melting point is actually the highest of those in comparison. Now, when we look at the second graph, so the graph on the right here, again, we're looking at fluorine, chlorine, bromine, and iodine are all in the same group. So they're all in group 17, okay? But we have a little bit of a blip here. So we would have expected that HF, that would be predicted based on our LDF forces. And then it would have looked the same as the graph on our left, right? So HF would have fewer electrons than HCl. HCl would have fewer than HBr. HBr would have fewer than HI, meaning iodine would have the highest amount of electrons and should have had the highest melting point. But we have this anomaly happening where our HF is actually a really high melting point compared to the HCl, the HBr, the HI. In this graph, this section here that I'm outlining in purple, that follows the same idea as the first graph, that HCl has the lowest number of electrons compared to HBr and HI. And so HI has the highest melting point compared to those other two because it's got the most amount of electrons. But in this one, HF has the highest melting point because it has hydrogen bonding. So when we're looking at intermolecular forces, it matters how many forces there are, but it also matters what kind of forces are in the molecule. And since hydrogen bonding is such a stronger intermolecular force than just regular LDFs, it makes a huge difference for the melting point. This is extremely important for us when we're looking at water because water has a really high melting point and boiling point compared to what it should be if it didn't have hydrogen bonding. Hydrogen bonding is the reason why water actually boils at 100 degrees Celsius, why it melts at 0 degrees Celsius. If we didn't have hydrogen bonding, the melting point and boiling point of water would be significantly lower. And so because it has hydrogen bonding, it has a significantly higher boiling point and melting point. Okay, I want to do a couple more examples here, just looking at molecules and deciding what types of forces they might have involved in them. So if we look at this molecule here, so we've got this molecule here. So we want to know what types of forces we have involved here. Now, always, LDFs should be your answer right away because LDFs are in everything as long as it's got electrons. This molecule has electrons because it's got atoms, so it has LDF forces. Now we just want to decide whether we maybe have ionic forces. Since we don't have a metal, we would say no ionic forces. So no ionic. And our reason for that is there's no metal. We need a metal to have an ionic bond. We need a metal to have an ionic force. So there's no ionic forces. But then I also see that I've got this oxygen attached to hydrogen on the end. And I know that that means dipole-dipole. Oh, I'm sorry, hydrogen bonding. So we've also got hydrogen bonding here because we have that oxygen attached to a hydrogen. Now, since we have hydrogen bonding, we don't have to say that we have dipole-dipole forces. We would always say that hydrogen bonding will trump dipole-dipole forces. Okay, so if we have a polar bond, we have dipole-dipole forces, but if we have that special dipole-dipole of hydrogen bonding, we don't need to say that there's dipole-dipole. We can just say hydrogen bonding. Okay, let's look at one more example here. So say we have sulfur. Let's do sulfur trichloride, so SCl3. So in this molecule, we of course have LDFs because we have LDFs in everything, okay? And then we actually want to decide whether sulfur to chlorine is a polar bond or not. So the difference in electronegativity between sulfur and chlorine is 0.5. So we know that means a polar bond. Since there's a polar bond, we have dipole-dipole forces. Okay, so we just need to have a polar bond to have those dipole-dipole forces. Again, we know it's non-ionic because there's no metal, and we don't have those special atoms that we need for hydrogen bonding, so no hydrogen bonding. So we just have LDFs and dipole-dipole forces. Now, if we wanted to draw the intermolecular forces between molecules, so let's try one more example here. So say I give you the molecule NH3 and say draw the intermolecular forces in NH3. What we need for this is we have to actually draw two NH3 molecules. Okay, so we need Lewis structures. For our NH3 molecules. And we know that NH3 molecules have partial charges. And so we're going to draw our attraction between a partially positive hydrogen and a partially negative nitrogen. And we know that is a hydrogen bond. Okay, but again, we need to show 2 molecules of NH3 if we're trying to draw the intermolecular forces. All right, so that's the video lesson for intermolecular forces. There are some practice questions to be working on, and that's it for intermolecular forces.